potential problem we're going to run into in these multi-degree of freedom systems when we're talking about the free vibration type of problems with initial conditions is that solving for all of the constants, those c values and those phi values, is going to become quite complicated once we have too many degrees of freedom going on. With the 2 degree of freedom systems, we were able to use fmin search, we were able to use a zero finder basically to solve for what those constants are. But as the dimensionality of the system grows, doing a technique like that is going to become very slow and maybe impossible for the computer to do very well. So alternatively, in order to find these closed form solutions, we are going to employ a technique called principal coordinates. And the premise here is that we are going to be able to decouple our system. So the problem with the closed form solutions is that we have all of these different driving frequencies happening at once, and we're trying to satisfy a lot of our initial conditions all at the same time. When we're in principal coordinates, we are going to be able to decompose or decouple our system, and we're going to see it's going to be much easier to find what those constants are supposed to be. So where we're going to go with this is that we are going to be able to change the coordinate system that we're doing some of our analysis in to one where every equation of motion has only one frequency, one of the natural frequencies in it, and we're going to see it's going to be much easier to solve. And it's not going to matter which coordinates we do our initial analysis in, as long as they fully describe the system and they are all independent degrees of freedom. We're going to be able to go from whatever that original coordinate system was to our principal coordinate system the same way. So notation-wise, we are going to say that our principal coordinates are this Q coordinate system where we'll have Q1, Q2, Q3, which are all going to be these independent degrees of freedom. And we'll have our one definition now. So our chi is going to be our collection of mode shapes. And originally, the scale of them is not going to matter if they come out of MATLAB or Mathematica. If they each have a magnitude of 1 or not, it's not going to matter. We'll just get that collection of chi values. And we're going to say that we can go from whatever our original coordinate system was x, so is that some x1, x2, x3, whatever was convenient to derive our equation of motion in. If we take this chi, our mode shape matrix or our modal matrix, and invert it, and then multiply it by x, it's going to give us q, our principal coordinates. So it's really just a coordinate transformation that we're doing, going from whatever the convenient or physical coordinate system was into this q principal coordinate system. So it will be a little bit more complex than this. We first need to take that modal matrix, and we are going to need to make the mass-normalized modal matrix. So the issue is that that modal matrix, the scaling of it is not unique. As I was just saying, in MATLAB, every mode shape is going to have a magnitude of 1. In Mathematica, the bottom entry is going to be 1, but we could scale any of our mode shapes by any value, and it's still going to be correct. It's just going to be a different scale. So what we need to do in order to do the principal coordinate analysis is we are going to have to find a specific scaling for those mode shapes, and that's where we use these mass-normalized modes. So what we're going to do is we take the chi values, that modal matrix, as we get it out of MATLAB or Mathematica, and we're going to take its transpose, we're going to multiply it by the mass matrix, and then we're going to post-multiply it by the modal matrix itself. And what we're going to get out of that is a diagonal matrix. Anytime we do this operation, we're going to get a diagonal matrix. The off-diagonals might be a little bit different than 0 just because of some rounding, but more or less it's going to be a diagonal matrix. And on the main diagonal, we are going to call entries on the main diagonal m1 squared, m2 squared, m3 squared, to mn squared, depending on how many degrees of freedom we have. Now, depending on the scaling of chi, these m1, m2, m3 are going to be different, and that's kind of the point here, is that we're going to be rescaling the values of chi depending on what we find for these m values. Because the next step is now assembling what I'm calling the mass-normalized modal matrix. So this chi sub n is designating that it has been mass-normalized. And what we do is we're going to take every column of chi, so that is each mode shape, chi 1, 2, 3 to n, and we divide every entry in it by the associated m value we found in the previous step. So again, the entries on the diagonal were this m1 squared. So now for chi 1, we're going to divide each entry in it by m1. So we're just rescaling it. And chi 2, we do the same thing for all of the mode shapes until the last one that we divide by m sub n. So I've not changed the mode shapes because I'm just rescaling them, but I'm rescaling them by this specific value. So by doing this, it's going to make sure that our chi sub n is going to be in a uniform scale. It didn't matter what the original one was. When we rescale it this way, we're always going to get the same chi sub n values. So what's the utility of this? Well, let's start to piece some things together and see some properties of the mass-normalized modal matrix. So two important things come out. If we take the mass-normalized modal matrix and take its transpose times the mass matrix and then post-multiply by the mass-normalized modal matrix, we will always get the identity matrix. So a main diagonal of 1s and off diagonals of 0s. So that's going to be a really useful property algebraically, as we're going to see in a moment. And if we take the mass-normalized modal matrix transpose, pre-multiply the stiffness matrix, and then post-multiply that by the mass-normalized modal matrix, we get another diagonal matrix, and it's the diagonal matrix of the squares of the natural frequencies, which were also the eigenvalues of m inverse k. But here we're going to be thinking of them as the squares of the natural frequencies. All the off diagonals are 0. The main diagonals are the natural frequencies squared. Now the utility is that we have these diagonal matrices. This is going to start to make the algebra easier when we enter this modal analysis. So going kind of in the opposite direction that I talked about a couple slides ago, we can go backwards and say that if we take this mass-normalized modal matrix, we pre-multiply it by q, the principal coordinates, we can get back to our original coordinate system, which was x, again comprised of x1, x2, x3, however many degrees of freedom we had. So let's take a step back and go to the original equation of motion we were looking at. So here for undamped systems, we could have forcing. The right-hand side could be 0. This is going to apply either way. In this course, we're really going to stick to f being the 0 vector, but I'll show it in this more general form. So if this is our original matrix form equation of motion, what I'm able to do is substitute in for x and x double dot this expression, the relationship between our original coordinate system and these principal coordinates q. So my chi's are constant. They are not going to be affected by a time derivative. So doing that substitution, we can see replacing x is going to be chi n q. X double dot will be chi sub n times q double dot, and that's just a simple algebraic manipulation. Okay, so that substitution is done. Now what I can do is on the left-hand side and on the right-hand side, I'm going to pre-multiply every piece of this, every term of this, by the transpose of my modal matrix. So I've done the same thing to the left as I've done to the right here, just pre-multiplying by this chi n transpose. And finally, what we can do is we just saw on the previous slide what chi n transpose m chi n was. We saw what chi n transpose k chi n was. We can do that substitution from the previous slide. We know that the first term is just the identity matrix, as long as we're using the mass-normalized modal matrix here. And we know that the second term, this chi n transpose k chi n, is going to be the diagonal matrix of the natural frequencies squared. So this omega n squared is a diagonal matrix, it's not a scalar. And then I is going to be, well, the same size as q, where it's going to be a square matrix with the same number of rows and columns as we have entries in q. And then I'm going to call this chi n transpose times my forcing capital Q. Now again, if we have a free vibrating system, that's still going to be 0 on the right-hand side. So it looks like we did a lot of algebra, we did a lot of substitution here, some matrix manipulation, but what did we achieve? Well, here's going to be the payoff of doing this substitution. We now have n uncoupled ordinary differential equations, because if we see I is a diagonal matrix of 1s, and this omega n squared matrix is also diagonal. So the nice thing here is that if we think of going back from the matrix form into the scalar form, every row of this equation has only one of the coordinates in it. It will only have q1 and q1 double dot in the first equation, q2, q2 double dot in the second, and so on. So why is this useful to us? It's going to be much easier to solve this series of ordinary differential equations when each one is only going to have some degree of freedom and its second derivative in it, rather than the original system where every equation of motion probably had all of our degrees of freedom and the second derivatives of all of our degrees of freedom. But now what we have using these q coordinates is a bunch of second order but 1 degree of freedom ordinary differential equations that have been uncoupled. So what's the benefit of that? Well, when we have a 1 degree of freedom second order system, we already know how to solve that. Relatively, it's really easy. Once we add in multiple degrees of freedom into each of these equations, that's when it gets difficult. So the solution for each one of these q's, the q1, 2, 3, and that's what the superscript here is indicating, is which principal coordinate is it, 1, 2, 3, 4, or however many degrees of freedom we have. We can find its solution relatively easily. Each one is going to oscillate only at its associated natural frequency. So notice here, we only have the ith omega term, or the ith natural frequency is what that omega is pertaining to. But what we're going to need to do is bake in what the initial conditions are. So we need the initial position, or the 0th derivative for the ith q value, ith q coordinate, and the initial velocity of the ith q coordinate. And finding those will just take one extra step, but we know that this is the solution for each one of our q's. So we can solve really easily q1, 2, 3, 4, etc. So we need, though, to get these initial conditions in terms of this new coordinate system, the q coordinate system. Well, luckily we already know how to go from our original coordinate system into q, because we can use that mass-normalized modal matrix to get there. So one of the last steps here is, if we have our initial conditions in our original coordinates, both for position and velocity, by pre-multiplying by this mass-normalized modal matrix inverse, we can get now our coordinates into these q, these principal coordinates. So then we can take this q naught and q naught dot, we can put those in the above equation, and then we can get closed form solutions for q1, q2, q3, and so on, the principal coordinates. So we have closed form solutions in our principal coordinates, but the downside is that the principal coordinates, their advantage is that they are decoupled, they're really easy to solve. The downside, though, is they don't really have a physical meaning to us. We're probably not going to be able to observe what are these principal coordinates doing. So the last step is, once it's in these principal coordinates and we have a solution, again, we know how to go back now to our original degrees of freedom, our original coordinate system. So once we have our q of t, now by pre-multiplying by that mass-normalized modal matrix, that will take us back into our original coordinate system, that there it does have some physical interpretation. So what's going to be happening here is q, remember, is each q only is going to oscillate at its own natural frequency. And what's going to happen when we pre-multiply by this mass-normalized modal matrix, basically that's telling us for each of our original coordinates how much do we need to mix q1, q2, q3, q4, etc. to get to our original degree of freedom. So x will be oscillating at all of the natural frequencies because it's going to, each x, take a mixture in different proportions of q1, q2, q3, q4, and kind of blend them together, superimpose them, and that gets us back to that original x coordinate system. So what's the point of all this? Why are we going through all of this matrix algebra, solving these uncoupled second order but 1 degree of freedom ordinary differential equations, and then we just go back to where we started, back into X? Well, that is essentially what we're doing, but here's why that is actually useful to us. So we start down here. We have a bunch of ODEs in the original coordinates. And again, the problem there is that we have several of these ODEs that are coming from our equations of motion, but each ODE has possibly all of our degrees of freedom and the second derivatives of all of our degrees of freedom. So where do we want to go? We want to go here. We want our solution to those original coordinates. We want to know what is x1 of t, x2 of t, and so on. So what we did in the 2 degree of freedom is we took those ODEs in our original coordinate system, and we were able to solve those n, in that case 2, coupled ODEs and get right to our solution in our original coordinates. So that was great for 2 degrees of freedom. We could use that F-min search or some other similar technique and solve all those coupled ODEs. But as we get to these larger and larger systems, solving those coupled ODEs is going to become extremely difficult, even for either for the computer to solve or by hand. Really, we're not going to be able to solve it at all. So it's really tough to go from this box to this box directly. So what principal coordinates lets us do is kind of bypass this tricky step, or this very difficult step, by taking a sequence of much easier steps, because we're kind of going to be changing a calculus problem into a linear algebra problem. And computers are much better at doing linear algebra than they are at doing calculus, and they're much better at doing linear algebra than we are. So what we do is we're going to kind of do an end around here. We're going to take our ODE in our original coordinates, and we're going to do this coordinate transformation. We're going to change from our original physical coordinates into our principal coordinates Q. And the beauty there is now having our ODEs rewritten in this new very specific coordinate system of the principal coordinates, going to the next step here where we solve these ODEs is now much easier, because this system of ODEs are all uncoupled. Each ODE has only, for example, a Q1 and a Q1 double dot. The next one will have Q2, Q2 double dot. And that's much, much easier to solve because it's just a series of n-DOF systems that we need to solve instead of down here a series of coupled systems. So going from this step to this step, that is pretty easy because it's only going to be oscillating, each Q is only going to be oscillating at a single natural frequency. So now we have our solution for Q1, Q2, Q3 in the principal coordinates. And now to get where we actually want to go, we do another linear algebra problem, which again, that step in itself is pretty easy. We use that modal matrix again, and we can go from this solutions in Q back into solutions in X, whatever that original coordinate system is. And we are able to arrive where we needed to go, getting this closed form solution in our original coordinate system, but we didn't have to solve a bunch of coupled ODEs to do it. We were able to do a linear algebra, a simple calculus problem, another linear algebra, and then get where we needed to go.